Yeah. So geometric isomerism is shown by two types of compounds. One compound with double bonds and compound with rings. So this is an example for a geometric isomers with the double bonds. This compound will show geometric isomerism, and they have a difference in properties. Example, I have given you fumaric acid and malic acid. Fumaric acid is having carboxylic acid group on the opposite side. Malic acid, carboxylic acid group on the same side. Fumaric acid is more stable than malic acid. It is having a high dipole moment, a zero dipole moment. It is not, because it is opposite. See, the dipole moment, direction of the dipole moment is opposite. And malic acid will be having a net dipole moment. One side will be positive and the other will be negative. And you can see the melting point is higher for fumaric acid, which is more stable. While malic acid, it's not the case. You have a lower melting point. Another thing is this cannot form an anhydride. Does not form anhydride easily. But this forms an anhydride very easily. That is what we had. See, this is the anhydride of the malic acid. See here. This is the mechanism of anhydride formation. Nucleophile, this is attacking, and one molecule of water is coming out. So H2O. Can you see whatever I am writing on the board? Okay. I hope you can see it in your mobiles. Okay. Now, so malic anhydride, malic acid can form easily an anhydride because the carboxylic acid groups are on the same side. COOH groups are on the same side. And so they can come together. See here. COH groups can come together to form a bond. And that is what's shown here. You can see that O oxygen of one carboxylic acid group attacking the carbonyl group, and OH is the leaving group here. Okay, so this is now the rotation. Now, why do compounds show optical this geometric isomerism? Because geometric isomerism, you have a double bond, and rotation around the double bond is not allowed. It is not possible. It will break if you rotate it. It's just like two ropes. Suppose you tie two ropes together on two sides. If you rotate this one of them, if you rotate only one of them, what will happen? You will get something like this. Is it not? Okay, and if you keep on rotating, this will break. So double bond rotation is not allowed. Rotation around the double bond is not allowed. But if you have a single bond, you can rotate this, that we have seen before. Okay, so that is why these compounds will show geometric isomerism. Okay, now examples of compounds of geometric isomerism. I've shown you one. You can make any bond, any compound. Say for example, look here. I got HCH3, double bond HCH3. This is a cis compound. Okay, what is the name of this compound? 1, 2, 3, 4. So it is butene. It is butene. Which 2 butene. Okay. It is cis 1, cis 2 butene. And remember this the IUPAC nomenclature is E2 butane. Sorry, Z2 butane. Z2 butane. How do you get the Z? Z means on the same side. E means on the opposite side. Now the geometric isomer of this compound is this one, CH3 and CH3 and H and H. So you have CH3 on this opposite side. So this is trans or E butane. E2 butane. But remember, one butane will not show optical geometric isomerism. One butane. This is one butane. C2H5 here and H here. One butane will not show optical geometric isomerism. Why? Because you don't have two groups on this carbon. So what? This is the requirement of a compound to show geometric isomerism. What is the requirement? Double bond with minimum two different groups. Minimum two different groups. This is very important. On the two carbons. The different groups should be on different carbons. On the same carbon, you cannot have the identical groups. See here, both are hydrogen. This will not show geometric isomerism because you draw the other form, you will have the same hydrogens here. Both of these are same. One and the same. If you just rotate this 180 degree, you will get this compound. So they are identical. Okay, the whole molecule will rotate. But if you rotate this molecule whole, if you rotate 180 degree, it will never come to this. Okay, so that is briefly about geometric isomerism. Now, how will you distinguish between geometric isomerism? That also I have mentioned. How will you distinguish? How to distinguish? Yeah, how to distinguish between them? Number one, melting point. Okay, geometric isomers are different compounds. They will be having different melting points and properties. Okay, second one, dipole moment. Dipole moment. And third one, formation of chemical reactions. Third one, chemical reactions, chemical reactivity. Chemical reactivity like Anhydride formation. Anhydride formation. So this is our discussion on geometric isomerism. Okay. Now let us discuss what is meant by optical isomerism. Optical isomerism. Optical isomerism. Let's see what is optical isomerism. Optical isomerism uh, is the ability. We'll put optical activity. First of all, optical activity. What is optical activity? So let me write optical activity. Optical activity. Optical activity is the ability. It's an ability to rotate the plane of a plane polarized light plane polarized light of a plane polarized light to either side when passed through when passed through a chiral molecule. A chiral solution of a chiral molecule through solution of a chiral molecule. Yeah, you have so many things have to be defined now. Okay. So what is meant by plane of a plane polar? What is polarized light? What is plane polarized light? That is one thing which we have to explain. Okay, and then we have to explain what is meant by the chiral molecule. Okay, now let us see what is a plane polarized light. Plane polarized light. See here, I have ordinary light. It's a small coil. So we have the ordinary light. I told you plane polarized light is an electromagnetic radiation. Okay, so ordinary light is also an electromagnetic radiation, you know that. Now, you have in ordinary light, you have all magnitude of wavelength. Okay, you have different magnitudes of wavelength. Wavelength will be different for different rays. So white light means, what is white light? It's a mixture of all possible uh, waves with lambda equals 400 to 700 nanometers, 300 to 700 nanometers. Okay, so what is the wavelength? Possible wavelengths? Lambda equals 300 to 500 nanometers. Oh, sorry, not 700 nanometers. So this is what is meant by a plain polarized light, a ordinary light. 700 nanometers. Now, ordinary light, as you know, it consists with gear. With gear. So here comes with gear V. Now, the V will be in the range of 300 nanometers. Or is it 700 nanometers? Which is V, while it is more stronger, which is more, you must be knowing it. Violet light will be having lower wavelength, higher energy, and red will be having higher wavelength, low energy. So here the wavelength is increasing. At the same time, the energy is decreasing. Same time, energy is decreasing. So this is an ordinary light. Now suppose you want to separate this light into specific wavelength. Only one specific wavelength. You want to generate a light with only one wavelength. You have two choices to generate light with one wavelength. What are the methods? There are two methods. Number one, use a separate source of light. Use a separate source of light, which will produce only the required wavelength. That is one thing. Example, sodium vapor lamp. Which produces a yellow light. Which produces a yellow light. Okay. Yellow light. Now the yellow light is, you must have seen the street lights in big cities. You can see big poles which are bent something like this. You have a tube like this sort of thing, or I don't know whether it is bulb or tube or whatever is that, it will be yellow in color. Many of you must have noticed it. That is yellow in color, that light. That is a particular wavelength. The wavelength of sodium vapor lamp is 589 nanometers. This is taken. Most of the measurements of optical activity, we use this light source, okay, as a source of monochromatic light. The second method is use a prism here itself. You keep a prism here. Okay, and then a screen here. When you keep a prism, you will get a figure here, V and R. Suppose you want only one light. Suppose you want only one light. What you do is you make a small hole here. A very minute hole through which only the required light of the required wavelength also will enter. Okay, light with only one wavelength will come here. Light with all possible wavelengths will be here, but you just make a small slit here, an opening. So only this light will come here. Only one type of light with only this wavelength range will come out. Okay, so small opening on the screen. Now, if you want to change this light, if you want to change the wavelength, what you have to do is you just rotate this prism. So this is a prism. Just change the rotation of this prism. The one which is coming, say this light will come here and will come out into our observation place. Okay, so this is a monochromatic light. Light. The second one there is prism. Okay. Oh my God. What happened? Your connection is gone. Are you able to see the board? Yeah. Let me share the screen again. Okay. Now see here. So this is sodium vapor lamp. And now second one is the prism, and you can use this. You can change the rotate this particular prism so that different wavelength will be coming out of from here. The internet is weak. I think after 10 or 9:30, the internet become very weak. I think we may have to start our class even still earlier. Okay, one second.